I guess I'll start now. Hello, everybody, and welcome to the first talk of the AI and ML Security Special Interest Group of ComSoc for the fall season. So we have today Professor Walid Saad, but before we get to him, I'd like to quickly introduce a little bit about the Special Interest Group per se, and generally some logistics and things. So I am Professor Subhasa Vilakshmi. I am a professor in the Electrical and Computer Engineering Department at Stevens Institute, as well as the founding director of CI, which is Stevens Institute for Artificial Intelligence. The vice chair for this group is Jola Saha, who is from Albany. And let's see, looks like I have the same issue with my, okay. So right now we are about 340 plus members. You can find us on LinkedIn. I have posted the LinkedIn link here. You can also search using our group title, which is Special Interest Group on AI and ML and Security in LinkedIn. Or you can, of course, contact either of us, Dola or me, via our email. All of the slides will be available in the SIG website. Our recorded talk will also be available at the SIG website. We just have recently started a YouTube channel, so these recordings will also be available on the YouTube channel for you to look at a later date if you want to. Just some quick logistics of the talk. Everybody is muted when you enter. Please stay muted throughout the talk, but feel free to type in questions for the speaker in the chat box as the talk is progressing, especially since we tend to forget things. So definitely go ahead and use the chat box. Our moderators, actually Dola, will be reading out these questions at the end of the talk for Walid to answer and for all of us to have any conversations. So today's speaker is, as I said, Professor Walid Saad. He will be speaking on, I made a mistake on the title there. I apologize, but he will talk about that anyway. So Professor Saad is a professor at the Department of Electrical and Computer Engineering at Virginia Tech, where he leads the News Laboratory, Network Science, Wireless and Security. He is also an IEEE Fellow. He is a recipient of the NSF Career Award in 2013. The Young Investigator Award from ONR in 2015, and he has won several awards, and I'm only listing a few of them here. He has won the 2015 Fred Eller SIG Prize from the IEEE ComSoc, 2017 IEEE ComSoc Best Young Professional in Academia Award, 2018 ComSoc Radio Communication Committee Early Achievement Award, 2019 ComSoc Communication Theory Technical Committee Award. He was also the co-author of 2019 and 2021 Young Author Best Paper Awards. He has, I think, at least 10 Best Paper Awards so far. So we will have some definitely exciting talks from Professor Saad today. With this, I'll stop sharing, and Walid, please feel free to take away.
Okay. So thank you, Subha and Dola, for the invitation. It's a great pleasure to give this talk today. So in today's talk, I'm going to talk about, more generally about distributed learning in wireless, but particularly I'm going to focus on a new framework that we looked at, which is more along the lines of distributed GANs. So I'll start with a quick one slide introduction on distributed learning, and then I'll jump directly into GANs and talk a little bit more about how we use GANs and what's the benefit from them, and then look at the idea of distributed GAN in more detail. So the first part is more on the learning side. There is no communication. And then I'll jump into how this BGAN framework can be applied to wireless. And I'll quickly talk a little bit about RL at the end and conclude. So as you all know, and I don't think I need to motivate this too much, we're moving from the era of a cloud-centric large data or big data towards what we can call small data that is distributed massively across edge devices. So this data is private and oftentimes it's local, so devices would not want to share it, or at least if they wish to share it, they wish to share it with some sort of privacy. So the question really is, can collaborative devices or collaborative users learn a task of interest, a machine learning task of interest together? Of course, a leading figure in this area is federated learning. and we've done quite a bit on that before. So federated learning is one original algorithm that talked about how you can do learning across multiple devices. How does that matter for us as networking or security or communication researchers? So the idea is, well, there's two angles to it. On the one side, in IoT, in wireless systems, we often need to do learning of resource allocation mechanisms, of scheduling, and so on. And there's a lot of need for distributed learning, like federated learning. So we can think of the first research area, a big one, here is to use federated learning at the edge to communicate. Now, on the flip side of it, future wireless systems and like 5G or even 6G and beyond, they are supposed to actually support federated learning algorithms. What I mean by that is you might have a set of users, like those in the figure here, that are executing a FL algorithm related to some task. I don't know, a computer vision task, a navigation task. And what they're trying to do is to use the wireless system to actually communicate their weights and all the metrics or model parameters from federated learning. Here we can look at a second thrust area, which we were kind of among the first to look at, is how does communication, meaning delay, error rates, channel imperfections, affect the performance of learning? And we advocate there for a joint design of the FL algorithm to maximize accuracy and of the wireless system to maximize reliability and latency, minimize latency. But in all of these across both, there's this angle of the agent learning, right? So there's multiple agents distributed at the edge that need to learn or use communication together in a collaborative way. And that's kind of motivates some of my talk today. So my talk today will be a little bit more along the first part, even though the first big section will be just learning. The second section is more along how to communicate with that learning. So what is a generative model and why do I focus on GANs? So in statistics, I'm sure the audience knows even better than me. There's these two main areas, the generative approach and the discriminative approach. Oftentimes, most of our work, even the original FL algorithm, is really discriminative. So we use discriminative models. Now, the difference is that in a generative model, you would be looking at the distribution of your observable variable and the target variable in a joint distribution. So you would be learning a joint distribution of the two, as opposed to a conditional distribution of y knowing the observation. So a generative model can give you an even more expanded view on a certain random parameter of interest. So generative models have been very popular. And among the most popular of them is the so-called generative adversarial networks. And the idea this is from Ian Goodfellow's original work. So the idea is he used two neural networks, a neural network that's called a generator and a neural network that's called a discriminator. The generator tries to generate an example of a sample from a data set that they're trying to jointly learn. And this discriminator tries to discriminate whether this is a real example or a fake example. What Ian Goodfellow showed is that this could be modeled as a zero-sum game, which is why we call them adversarial. And then he can show there is a Nash equilibrium for that game and that the GAN could work the way we'd like it, which is essentially generating data points from a distribution of interest. And of course, a very popular example of GANs is this generation of fake celebrity photos. Even the deepfake videos have a certain GAN within them. So the question we ask is the following. Federated learning has been around for a while, but can it apply to a GAN rather than to a general neural network? So can we create a distributed GAN? So existing GANs, all of them, in fact, including info GAN, conditional GAN, there's a lot of flavors now around. I cannot keep track of the names. They're all centralized in the sense that they assume the entire data set is at a certain location and you're running the generator and discriminator there. So what if the data of interest is like an FL, distributed across the agents, scarce, so you only have partial data, and private? I'm gonna get more into this. So our work does not target privacy directly. So we have some sort of privacy, but there's a lot to do there. And essentially you'd like these collaborative devices to use GAN to generate data points from a common distribution without sharing the raw data, without relying on a central server. So completely distributed. So what is out there? So of course, the first idea that came to our mind was applying federated learning as is to a GAN, but that was done by others already. And this is called FL-GAN. The idea is you have generator and discriminator at a parameter server, you have a generator discriminator at your agents, you share the model parameters just like in FL, and you do updates back, and they showed that this can work. The only issue is that it's not fully distributed. So it still relies on a parameter server. There are other competing algorithms. One is called MDGAN and one is called F2UGAN. This is a special case, this one. The idea was that they wanted to have only a single generator. So they eliminated the generators at the agents. They have only a single generator. And again, they do something similar to FL, but now they have less communication because they have a generator only at the central server. And the difference between the two is one of them uses collaboration between the discriminators here, one of them doesn't. So they're kind of similar architecture. But still, these are limited. So the first limitation is they both need a central controller, and they have expensive communication requirements, especially for MDGAN and its variants. FLGAN, it depends. I'm going to talk about it later. So, and they're limited in the sense that you cannot have different neural network architectures. And why does that matter for IoT? Because in IoT, you might have a server connected to the IoT and also a small sensor. On the server, you can use a highly sophisticated CNN with like thousands of model parameters, but on the sensor, you might need to use something very small, like a binary neural network or something. So this is not accommodated by any of those, neither by MDGAN, neither by F2GAN, neither by F. And the agents in the MDGAN and F2GAN case do not own their generator, so they're relying on a third party to give them their data points. So the question we ask is, can we create a fully distributed solution that is inspired in some sense from federated learning with heterogeneous agents in this? And the answer is yes, and this is the original paper. So the idea, we call it brainstorming GAN, it's the following. It's really a very simple idea. The idea is that we have a private data set at each agent, and we assume the agent owns their generator in this case, so you have their own generator. And instead of sharing the model parameters like FL does, which has its advantages from a privacy perspective, but also has its drawbacks from a performance and from a kind of accuracy perspective, we said, well, how about a kind of a middle ground? We don't share the raw data, but we share the generator output. So the generated output, which is a fake data, it does come from the distribution, and that's kind of where privacy can be further enhanced if you add differential privacy there, but we don't do that. But at the end, this generated point is still a fake point. And if you think about it, initially when these agents start to generate fake points in a GAN, they really are generating noise. So the information is not that critical. So what happens here is we said, well, let's share the generated output, which we call an idea. And this is where brainstorming comes from. In the sense that when I'm discussing with you, I have some original data, original idea in my brain, but I don't really share that. I don't know how to. I share a representation of it. And that's kind of what's happening here. The generator is sharing a representation, an idea based on what the private data set. So this is our architecture. It's essentially very simple, but we allow you to share the generator output between the agents. And of course, there could be communication constraints. So not all agents are connected to each other. So the benefits is we can show that this could be fully distributed. You don't need a central aggregator. You can have different neural network architectures for the generator and discriminator. So you can have this capabilities, device capabilities, tailored neural network design. And it will have less communication overhead. I will show it later. It depends on the dimension. So there are cases where we're better. There are cases where we're worse. In terms of privacy, I would say it's not fully private. So there is there are enhancements to be made there, but we are comparable in some sense to the privacy of the original federated learning algorithm, the kind of basic. So theoretically, what does this mean? So remember in Ian Goodfellow's work, it was a two-player zero-sum game. So we have something similar here. We have the brainstorming game is a multiplayer zero-sum game in some sense. So now your value function, which is the function that measures your reward, if you wish, for the generator and the discriminator, is function of the discriminator of I, of user I, the same agent, the generator of agent I. So without this term, this would be Ian Goodfellow's original derivation. But now I also get the generator from others, from J, other neighboring nodes. And this, again, this is directly from the paper of Goodfellow, but we add to it the others. So those are included here. So PBI is a weighted sum of the data points received from other agents, from your collaborating agents, okay, a mixture of the data. So the generator aims to minimize this value. The discriminator aims to maximize it. Here we have multiple generators and multiple discriminators. So it's basically a multiplayer zero-sum game with all these argmin, argmax. So we're trying to solve this problem. It is clearly, again, theoretic problem, and we need to find the equilibrium of this game. So can we find an equilibrium? The answer is yes. So a quick glance on the theoretical results. First, we need to find the optimal discriminator. Turns out it's a very simple combination of the distribution of agent I's of the current agent, his own data, and this PBI that I mentioned before. So it's a very simple result. And then with some mathematical elaboration and so on, we can show that the game has a unique Nash equilibrium where your generated point, your optimal or equilibrium generated point are essentially a weighted sum of the data points of others, essentially. And lambda here, it depends on the graph structure. And this is interesting because this links directly to the wireless connectivity. So it depends on who you're connected, because at the end you have a graph of agents, how you can design this lambda, and the Nash equilibrium will be affected by that as well. So this is, again, I did not spend too much on the theory here. So the proof is elaborate, but it's not, it doesn't have anything really significant to show as opposed to the result. So the experiments are going to be very interesting. So we take unless I state otherwise, I will use a ring graph topology, which is just very simple, meaning you connect it to your neighbor. And I'm going to use 2 or 3 types of data sets. One is a very simple ring data set, which is nice to illustrate. The idea was, this was where we generally started from this problem. We said that if you have 2 agents, one knows half a circle and one knows the other half, can they brainstorm to generate a full circle? So a full ring in this case. So this is easy to present, and it will show a lot of interesting results. I'll also use MNIST database and CFAR10 for some of these. So first we compute the Jensen-Shannon divergence, which showed me how close you are to the real data set for the different number of agents, different number of data samples. You can see that if you have a standalone agent with 1,000 data samples, you have kind of the best result, and that makes sense. If everything is centralized, if everything is available, then you don't need collaboration. But then more agents would compensate the lack of data. So you can see a trade-off between having more neighbors and less data sets, and that kind of helps to see how you can do better with multiple agents. So for example, a GAN with 10 samples has a JSD of 24. If we multiply that by 10 agents, we have a JSD of 13, because now you have access to more data, and you're just basically exchanging this generated data points. Now let's look at this comparison with the link. This is also with the ring data set. So the number of data sets per agent in the y-axis, and then you have a standalone GAN, a BGAN with 5 agents, a BGAN with 10 agents. You can see that with 5 agents, only 50 samples are enough, and you recover the circle. In a standalone, you need 1,000 here to get to something that's reasonably good. And with 10 agents, even with 10 data points each, you're very close to the original distribution. So you can see there is already a closeness in your output. So in terms of the, again, JSD versus the number of neighbors, here I show the number of samples. First thing to see is the pink curve. The pink curve says that if you have enough samples, you don't need BGAN. You don't need federated learning, just do centralized GAN, right? Because that's the best you can do with samples. Now, the less samples you have, the more neighbors you need, and the better you can do by doing this brainstorming with other GANs. Now, in terms of this heterogeneous data sets or heterogeneous neural networks, what we did is we used 5 agents with different number of trainable parameters. And you can see that a standalone agent, they don't do very well, each of them, so without collaboration. If you collaborate, all of them, they can recover your original distribution. They have a very low JSD, and this improves significantly. I do not compare with FLGAN and MBGAN because they simply cannot do it. So if you want to try this scenario with FLGAN, typically it doesn't work unless you do extensions to those algorithms. Now, back to the question I mentioned initially, can they brainstorm? Can they kind of own partial data, but generate data that they don't own? So the answer is yes. We did it first for the ring topology, 2 agents, everyone owns a half. If they do BGAN, they can own the entire distribution or generate it. What about the MNIST database? You can see here we have agents who own digit 0, 1, 2, 3, all the way to 9. We don't use a circle graph, we use a more connected graph here. So you can see agent 1 or agent 0 can generate digit 0, but he also can generate digit 1, 8, 1, 7. So he's able to generate digits that he does not own. So he's able to generate data points from the entire distribution. Now, of course, the frequency of the data points depends on the weights, depends on the graph, and so on. You can see it as well, like in digit 9 here, you can generate 2, 1, 3, and so on. And additionally to that, if we look at the CFAR10 database, we can see the same result. So agent who owns airplane here, he can generate pictures of birds. He can generate pictures of buses. The agent who owns truck images can also generate pictures of airplanes. So you can see you have partial data. This is the whole idea at the end. We have partial data sets, and we're trying to be able to generate a more complete distribution without having to use a central server and with some sort of privacy. Not fully private, and I did that from the beginning. So compared with BGAN, compared with FLGAN, MDGAN, and FTU, on the ring data set, you can see we have a much better JST. This is the green curve. And the black curve is your centralized, best case, everyone owns everything scenario. So we're not too far from it. And we can compare the FID as well, which is another metric between our algorithms. And we can see that BGAN is much more smooth and much better in terms of average FID on the MS database. Now, in terms of communication resources, so we can analyze that. So it's function of the number of agents, the batch size, the data size, and the neural network size. So first, BGAN is only function of the product of the batch size, the data size, and the number of agents. So it's clearly better than MDGAN and FTU GAN. So clearly you can compare this one with MDGAN, with FTU GAN, we're much better. Now, compared to FL, it depends. So it depends on what your data set is. As you know, in FL, in many cases, you might be able to have a smaller neural network than what you have in the data set. But in other cases, it's not the case. For example, AlexNet image database, this metric is larger than X. So it depends. I would say, is BGAN better than FLGAN in terms of overhead? It depends. The question is BGAN better than FLGAN in performance? That's always the case. We can show that. So in summary, and I'm going to move now towards more of the wireless part. So we showed that you can have a distributed GAN model with partial data sets and no centralized control. What can we do next? This is a SIG on security, and I think there's a lot of things to do here on security. Inherently, GAN itself may have a security leakage. So this is not because of BGAN, but because of the fact that GAN takes a certain distribution. So there's a lot to do there. How do you enhance security and privacy of a certain distributed algorithm like this one? You can also use this for inference. For example, we used it in an application where we used it for intrusion detection. So we use a distributed GAN to do intrusion detection in an IoT. You can also look at more sophisticated network connectivities and graphs. I'll touch a bit about it today. Again, I mentioned the intrusion security application, and we can apply it to many wireless applications. I'm going to talk a little bit about channel estimation or modeling in a minute. So let's see an example application from those, which is the last one along the lines of a wireless network. I'm going to consider a UAV assisted wireless network. So you have UAV base stations that are trying to communicate with ground users. Why UAVs? Because in a UAV network, there's a lot of mobility, and it's very interesting if you can create a spatial and temporal map across the channel models or the channel that you might encounter in that system. So we consider a set of IUAV base stations collecting channel information. It's a high frequency millimeter wave service, and they're trying to estimate the channel parameters. Wireless modeling is very standard. So you have this standard channel model with the antenna steering vectors and the channel gain. We have L path, but for simplicity, I'm going to assume a single path, even though the results really extend to L, to any arbitrary L. It doesn't really change too much. So we're going to assume a narrow beam and directional radiation. And then we will try to estimate essentially this, which is your channel gain across space, X and Y coordinates, and time. So we're going to assume that the angles of departure can be estimated differently. We can add those later, but for now we assume those are estimated differently. So this slide is very traditional, so I don't no contribution here much. We're just gonna show what I want to show from this slide is eventually our estimation problem is we're trying to estimate this channel over X, Y, T, and phi K. Phi K is going to be assumed to be given. So we're trying to estimate this channel gain. And so our data set, the observable data set at each UAV is essentially a three-dimensional coordinate time point with the observed data channel and the observed angles of arrival. So given these data sets, every UAV owns its own data set. Here, we don't want to share them because of distributed, we don't want to have a centralized solution. Privacy may not be a big deal here because this network is owned by the same operator, so you can share channel models. It's not a big issue. The bigger issue here is being able to do a distributed estimation. So we assume a conditional GAN, and there's a conditional sampler at every. So this is a single agent, the local agent problem. He will sample a AOD pair, and the generator will create samples knowing this the angle of arrival, angle of departure. He will generate the samples we need, and then the discriminator is just a discriminator here. It's a zero-sum game with conditions, so it's similar to what I presented before. We just have the conditions like here, which is fine. It doesn't change in BGAN. So we're going to implement BGAN essentially, the one I presented before, but with the only difference here is you have a conditional GAN, and second, which is a bigger difference, in my previous framework, I was assuming that, well, you can have a random arbitrary graph. Here, the graph is the A-to-A connectivity, air-to-air connectivity between the UAVs, so it's not arbitrary. And we're going to optimize that, and I'm going to show it in a minute. So again, it's a BGAN-based channel modeling. I mean, this slide is the same as BGAN. I just reformulated to fit it into the frame. So this slide doesn't have anything different except this remark that the air-to-air links are available, and these air-to-air links create the connectivity graph that governs what BGAN can or cannot do in this case. So we have to model the graph with a set of UAVs and edges, and at each iteration we just share eta, which is a kind of a parameter that we control, SI generated samples. And the first question is, can we quantify convergence, right? So does it converge? What we show is the following, and this is a significant theoretical result here. The probability that your BGAN converges after iteration K could be zero if T is less than L max. So L max is the maximum shortest path. So it depends on the maximum shortest path in your air-to-air network. If you're, below that maximum shortest path, you cannot converge. And then you can show, and this depends then on how much you share, your error probability locally, the number of agents, and some other parameters here. So you can see the probability of converging after T depends a lot on the graph architecture. So we can find it in closed form. It's dependent on the number of degrees, dependent on, again, epsilon, eta, which is this fraction of samples that I share, on Lmax, and also on this Lmin loop here, which is the shortest loop path. So we can give you analytically what is the probability of convergence, and that allows me to actually calculate the convergence time, which allows me to pose a meaningful problem that is more wireless than learning oriented. So again, there are some coefficients here that doesn't matter too much. So the probability of convergence decreases with the length of the maximum shortest path. So as this increases, the probability of convergence decreases. So you really want to minimize the maximum shortest path in your network. The number of iterations that we can need for convergence within a certain confidence level, p tau, is this one. And then we can quantify the convergence time. It's nothing but TJ, which is this confidence level based number of iteration, multiplied by the time you need to do the local training with a certain error, and the time you need to transmit. So this is the wireless link delay. T tau is the wireless link delay. So now we can pose a very interesting optimization problem on top of BGAN. We're trying to find the graph, the connectivity structure that minimizes convergence time, subject to the power constraint, SIR constraint, transmission time threshold, and some interference constraint. So we're trying to make sure that we have a graph with no interference as well in the air-to-air connections. So this is a centralized problem, and we were able to show that you can propose a distributed solution for it. This initially needs an assumption that the number of UAVs is equal to the number of edges, but we can relax that assumption later to maintain the distributed solution. So this is an optimization problem. We can show that with reasonable complexity, it can be solved in a distributed manner. No learning here, there's no ML or anything. It's just a optimization-based solution. So now what we know, in recap, we have a BGAN system that allows the UAVs to estimate a spatio-temporal map of their channel, of their millimeter wave environment. And we can minimize the convergence time of that algorithm by picking which air-to-air links will be active at a given point in some sense. When I pick a graph, it's really saying who should communicate with whom at a given point. So some simulation results, we're showing the probability of convergence versus the number of iterations. And the number I is the number of UAVs, B is the number of resource blocks available for the air-to-air communication links. So you can see more communication resources, we can converge faster at the expense of more spectrum, and more UAVs in this figure here. More UAVs, you can also converge faster, but you need more communication. You need more. Sorry, you do not converge faster. You need more communication resources to actually converge. So the larger network obviously needs more overhead. And that's kind of opposite. And then we can show versus this eta, how much do you share? If you are able to share everything, I mean, or many samples, then you can converge very quickly. But still, if you don't share a lot of samples, you still can converge reasonably well. So 25 iterations is not particularly too bad. And this is just function of the error training. So this is just to show robustness to the local training errors at every device. Because remember, this is at the end of distributed learning, you have local iterations and distributed iterations. And in terms of the average JSD, again, we can show that we're much better than the local CGAN. We're much better than the MDGAN and FLGAN. We're close to the centralized solution. And in terms of overhead, in this case, we're better than FLGAN. Of course, that again, that's dependent a lot on what you're sharing and so on. So this is not a general result. It's particular to what to our model. So and finally, we can show actual network performance. So compared to any other distributed solution, we're much better in the average rate, and we're not too far from a perfect CSI where you have everything available. You don't learn it. So there's some difference but it's not a significant one. So I will, before I conclude, I'll go do a quick glance on a different angle of GAN used with reinforcement learning, not federated learning. So this is a very quick glance on this one. So the idea here was the following. We talk a lot about ultra reliable low latency communication, but almost exclusively, most of the prior work in this area has been looking at IoT sensor uplink short packets. And they assume no models for the traffic, like Poisson arrivals. And even if they consider deep reinforcement learning, they don't consider the case where you have extreme conditions. What do I mean by that? Well, the moment you say reliable communication, even if you use a 3GPP definition, that means you have to be resistant or resilient to basically deepfakes, surges in traffic. So you have to guarantee 5.9 reliability. What the works that use DRL before for reliable low latency communication do is that although they improve after convergence, they improve URLRC, but they don't consider the fact that deep reinforcement learning is not really reliable. So if you use the one from computer vision, it's not really reliable. How can we improve that? And they assume that rates can be ignored. This is not necessary, and that's not a big part of my discussion. So what I'm going to talk about here is there's two open problems, I think, in this area. One is how do you make deep reinforcement learning resilient? Second is how do you make your latency numbers physically meaningful? And there where control comes into play. This is something I'm not going to talk about today. So again, a very simple problem. You consider downlink of a OFDMA system, and we will pose a problem of basically resource allocation, where we assume we don't have a delay model. So it's a model-free assumption because delay is hard to model anyways. So there's no models in the system. And this problem is very classical. It's really classical. You're trying to find power allocation, resource block allocation to minimize power, subject to feasibility constraints that are very simple. But this is the key. This is the cornerstone here. We want to have a reliability, which can be translated to the probability that your delay does not exceed the threshold. So we want to make sure that there's high, and with 5 nines, our delay is below this threshold. So this is the gamma I star. This is reliability. If you have models, then you can model this with Lyapunov optimization, something like that, and you can have some interesting results. If you don't have models, you have to use DeepRL. And that's probably the best solution you can do. The only issue with DeepRL, as I mentioned, classical DeepRL is not designed for low latency reliable communication. So what we propose is the following. We take a DeepRL framework, a deep queue, really simple for now. We use it, we couple it with a PPO algorithm to reduce the action space. So this part here, PPO plus what we call action space reducer, this is our own naming. It's not very creative, but it works. So this just reduces the action space using optimization. So we reduce the action space, and this is a first contribution. Not gonna dwell too much on it because I'm interested in this one first, more. So DeepRL is inherently unreliable in face of rare but extreme events. So our idea was the following. In order to learn events that you don't see all the time, the best way to do it is to gain experience. In machine learning, that means doing more training. The first thing that comes to mind is train this algorithm offline. But the moment you say that, as wireless people, we often know, there's no data to train with. I mean, nobody will give us data. Most of us don't have access to data. And data you find online is often not very useful to what you want to do. So if you don't have real data, gaining experience offline is not very meaningful. You can use synthetic data, but that doesn't do very well. So we said, what if I have some real data, a scarce data set of real unlabeled information, And I have the ability to create synthetic data that's very nice, but it's not always real. Can we combine the two to create experience and then train that deep RL agent in this experience, and we call it an experienced deep RL agent. So this is what we did. So we looked, and it turns out that Apple looked at this problem before from a different perspective. They were saying we have, again, unlabeled real images of eyes looking in different directions. And what they want to do is they can generate synthetic eyes, but they want to refine those with the real data to generate synthetic eyes or to generate new eyes that are looking in directions complying with the real data. And they proposed something called GAN refiner. And that was used here in this kind of application. We use it in a different way. So we adopted this refiner characteristic. We have unlabeled real information. In our case, it was packet arrivals and channel. And this is very limited to data. We have synthetic data from models, right? You can generate those in simulator. And then we use the refiner to have refined channel and packet arrival data. The beauty of this is it allows two things. You have now control over the data. We can show mathematically, you can prove like how much are you compliant with the real data, how much are you close to the synthetic data, and so on. You can control it, but you can also comply with the real data, and you can generate more. And that's really the whole idea of GAN. But on top of that, we're not interested in generating fake celebrity photos. We're interested in the deep RL agent. So we couple this with deep RL. So we tell the deep RL agent, you can now train here. Instead of training on only real data or training on only synthetic data or doing online training, which is not often good in wireless because of the transitory aspect of it. So doing that, we can show a quick result here. We run our algorithm. At epoch 100, we introduced a traffic surge. So we manually introduced the traffic surge. You can see the red is our agent. The black is a traditional deep RL agent. Blue is a deep RL agent trained with the real data. Green is deep RL agent trained with the synthetic data. You can see that at the end, the outcome is the same. So if you don't have reliable low latency communication, you don't probably care too much. But if you want to be reliable during the transitory period here, which is significant, you can see that a traditional Q learning is not great. Training only with one set data set is not great. Ours is very smooth in the transition. It's nearly constant. So you can see it transition quickly to the outcome that the learning can actually reach. And with this, I'm going to kind of conclude with an overview of other things we're doing. So we have a lot of things on the 5G aspect. I talked about low latency. I have a group of students working on these two aspects, terahertz communications from a networking, not physical layer perspective, and semantic communications from a learning meets wireless aspect. We have quite a bit of activities on AR with wireless and learning. We've done quite a bit on drones, vehicles, and I touched a little bit about it today. I have a group of students also looking more on the learning aspect itself, so like BGAN and other approaches. We also have a kind of an ONR MURI grant more on age of information and value of information in a network. I talked before a bit about communication for learning. We've done quite a bit in that. And I always do gig theory, so that's always in my slides. I have one student recently looking more at quantum communication and how do we leverage learning and optimization in such systems. And finally, I think distributed learning is an exciting area. There's too many things to talk about. And we tend to think about it as federated learning. I think federated learning is a little bit kind of mainstream now. We should think beyond that. Generative models are one way. There's other things to look at as well. And the field of application is abundant. I think security, there's a lot of things to do. Privacy, there's a lot of things to do as well. And finally, I can take the questions now.
Thank you, Walid, for this wonderful talk. So let me go ahead and read some of the questions that we have. And from the guests, please post as many questions as you want in the chat window. So the first question that I have is, have you studied how less efficient is communication-wise to exchange GAN output as compared to exchanging the model weights directly?
Yeah, we don't have a theoretical result. What I know is this, that let me go back to this slide. That in our case, BGAN is dependent on the size of the data, right? So it depended on that. So if the size of the data is less than the size of the neural network you need, then BGAN is better. If the size of the data is larger, then FLGAN is better in terms of overhead. But again, keep in mind, we tend to say FL is always better in that respect. That's not true. It depends really on the type of data you're dealing with. So usually for mid-sized data, probably FL is better. For very large data, it can be BGAN is better. For very small data, they're comparable and somewhat within the same range. But it really depends on how your neural network design compares to your data sets. It's really very direct.
So the next question is from Suba. So her question is, where does the optimizer lie on slide 26?
Okay, let me check which one. I think that is the. So it's the, I mean, yeah. The distributed solution we propose is per UAV. So the UAV, if every individual UAV has some, think of it as a distributed learning, distributed optimization solution for a convex. It's not convex, something like that. So the UAVs, every UAV contributes to that, so to solving this problem.
So do you have sorry, I'm just doing a follow-up on that.
Sure.
Do you have any complexity constraints on that, like on your optimizer? So do you have any reasons to believe that there will be something like that?
Okay, so I don't recall the exact complexity we have. I remember it was reasonably fine compared to kind of alternative like ellipsoid method and so on. But the reason we do it is because we're assuming from the start that you don't have a centralized controller of the UAVs. If you do have one, then he can still solve that, and then you don't need to do distributed. What we did, though, we did have to assume this one, which is that the number of UAVs equals to the number of edges, but we were able to relax it with a suboptimal, less efficient solution. We can relax it.
Thank you.
So the next question comes from Shubham Chakraborty, and he's saying, how do you control the GAN refiner on slide 36 that balances the bias towards the simulated data and limited real data?
So I don't have the equation here, but if you want, just give me a second. I'll share another slide which would show this actually. Just give me 1 second. I'll find it. To make my explanation easier. Yeah, let me share this one. Okay, so here, so you have this optimization problem actually. So there's this optimization problem here for the refiner, which is trying basically to optimize the neural network weights and the discriminator. So the refiner and the discriminator weights. And there's this epsilon R here, which is essentially telling you how close you are to your synthetic data. This epsilon R can be controlled, and we can prove that it actually has a lower bound. So this theorem is stated in the negative. So the refiner cannot be trained if epsilon R is less than this. So this is a lower bound actually. So with this lower bound, controlling the lower bound, controlling epsilon R, you can do it. We also think there is an upper bound, but we couldn't find it mathematically. I think there is one, but we couldn't prove it.
That's very interesting. So this becomes a hyperparameter for the system.
Yeah.
Okay.
Do we have any idea of how close this bound is? Like, is it tight?
I think it should be tight. We did not evaluate it actually, but if I remember well, it is kind of tight. We didn't have to do a lot of assumptions to find it.
Okay.
For the upper one, it wasn't possible. We had to have something very good so we did.
Sounds good.
I don't see any more questions from the audience, but I just have a quick question. In one of the the final few slides, you had mentioned that you are choosing some of the links over another. So you have an optimization where the links are chosen. So why do you truly need to choose, and why not use something like a broadcast kind of message so that you can utilize as many links as possible?
Yeah, so I mean, this just goes back to cost, right? Energy efficiency, power transmission. You don't want all the AVs to communicate with everybody because that just has costs in terms of computing, communication, and so on. So we try to find the one that minimizes my convergence time. Also keep in mind that some graphs might have worse performance in terms of the learning. So there's a coupling between the two. So it's better to find an optimal one or suboptimal. But yeah.
So I have one more question from the audience. That's great. How can GAN be applied for spectrum identification? Given an observation in a frequency band, how many radios and what kind of signals are transmitting, like Wi-Fi, LTE, satellite, LoRa, etc., such that you can zoom in on the one desired signal?
So this is interesting. I think I've seen works on that before. At the end, the GAN can learn a joint distribution. So you can learn a distribution of your signals of your transmitters. What I've seen people do is they use the discriminator of the GAN, which actually distinguishes between two things. And they feed it some information like on spectrum, and it can tell you whether this is an anomaly or not. Now you have more, probably in this case, you have more than a binary decision. But that's one trick that I've seen commonly used when you're doing identification with GAN. So that could be something to look at.
That's great. I don't see any more questions, but I would really like to hear from you if you have any thoughts, mostly on how to get data that is useful data for wireless channels. Because a lot of these problems that we are working on these days, they sort of depend on real data. And for image domain, it's extremely well defined. You have a ton of data that is labeled that we all know.
So I think there's a 3-tier here. There's some people who are really privileged who can get actual data from operators. I'm not one of them. So I've never had someone offer me data and say, you can use it. The other, the middle ground is where we rely at is sometimes we find online data, let's say on Crawdad or so on, which is very close to what we're doing. Sometimes we manipulate it a little bit. But I think what we're trying to do recently is create learning algorithms that can generalize well, which means in an ideal world, they would be training free. Can you kind of send a little data and actually make more sense of it through a better design of the neural networks, through approaches like meta learning or something of that derivative? So I think the interesting angle is to make learning algorithms that work better with small data, because I don't think we're ever going to get the data we need.
So what's your take on using some MATLAB generated channel models and some of those to sort of generate synthetic data and then try to work on that?
I think that's what most of us do, right? And I've seen good work. I mean, there's a lot of like some of those MIMO works and so on. They've got some meaningful results by using ray tracing simulations or some output of that. I think that works. But ideally, we'd have actual data.
Yeah. I don't see any more questions, so I'm assuming that our audience doesn't have any more questions, but I would really like to thank you, Walid, to be here and talk about this important aspect. And overall, I think it is very, very important for all of us to understand the challenges that lie ahead of all of us to move forward in this wireless domain.
Thank you so much. Thank you for the invitation again.
Thanks, Walid. As always, it was a fantastic talk.
I think I have one more question from Walid.
One more question, good.
So a shameless plug, if I may, we are in the process of thinking how ARA wireless can help the community with wireless data. If you may have any suggestions, please do feel free to reach out to us. So it's not truly a question. Thank you, Hongwei. I think
contribution.
Yeah, it's a contribution. Yes, absolutely. So thank you so much. And we will post the slides. If you can send us the slide, we will post the slides and the video of the talk.
Sure. Thank you so much. Thank you. Bye.
Thanks, everybody. Yeah.
Bye.
Thank you. Bye.